Okay, so welcome to video 2 of Unit 4. In the first video, we looked at impulse loads, which looks something like an instantaneous impulse, which we denote by this arrow at some time tau. And that impulse's magnitude is usually described by its area, which we called I. Now, the response to such an input, or a loading function, looked like a free vibration response whose initial slope or initial velocity was dictated by that impulse and actually was equal to I over m. Now, unit impulses are great because they can be used via superposition to describe almost any, or actually any kind of loading function possible. So in this video, we're going to be building off of impulse loading to derive the analytical responses to both step and ramp loads. And these can be used also as building blocks for more general functions. And so they're nice to have in your back pocket in these situations. Now, the goal for the first part of the video will be to obtain analytical expressions for both step and ramp loads. And we will do that as a two-step process. First, we'll express the force as an analytical function, and then we'll use either equation of motion or Duhamel's integral to derive the analytical response u of t. Now, I specifically recommend you guys to focus on the Duhamel's integral and derivations, because these will be extremely useful for understanding how to generally apply Duhamel's integral to almost any scenario. Now let's start with responses to step loads. On the left-hand side, from the image, we can see that a step load is defined as a loading function that goes from 0 instantaneously to some value p naught. And it does that at time equal to 0. This is pretty easy to define analytically, which we see above. So p of t is equal to 0 for any time less than 0, and it's equal to p naught for any time greater than or equal to 0. Now, skipping to the solution, we see that it will be the response of any system to this type of loading will be equal to some static displacement, which will be essentially have the very same form as that load. And that static displacement will be multiplied by a 1 minus some damping envelope, exactly the same as the free vibration situation, and then some oscillating function in terms of cosine and sine. Okay, so in essence, what we get is that the response actually oscillates around 1. And that's exactly what we see in the illustration. So we see that the response starts at 0, but then ends up oscillating around the value of 1. Right? That's because we have a constant force applied throughout the time. So essentially what we're doing is we're shifting the point of equilibrium for the free vibration. Okay, so let's see how that response is obtained. And I will just go over this very quickly. I encourage you to look in Chopra or in the Inman book for more details on how this derivation is obtained. One way to do it is to use the equation of motion directly. And in this case, for any time greater than 0, we have a non-homogeneous ODE, meaning that we have some sort of loading function on the right side. As we've done before, we can split that into a particular and complementary solution. The complementary solution will be simply the free vibration response, and the particular solution will be some constant. Okay, and so the first thing we need to do is solve for that constant. So we plug that particular solution in, and we get that that constant is equal to P naught over K, right? That's our static displacement. So we could also call this U sub st naught. And then we solve for the initial conditions, right? Keep in mind that it is not correct to assume that A and B are the same as the free vibration constants, right? So I'm just going to emphasize that. Right? So we need to solve for them again using the new solution. So we need to solve for them again using the new equations, right? And if we do that, we'll see that A is equal to negative P naught over K and B is equal to 0. So our final solution looks something like this, okay? Keep in mind this is for the undamped case, right? So it's going to look a little bit simpler than what I showed in the previous slide. Now for the same derivation but using the Duhamel's integral, actually turns out to be a much simpler solution. And that's one of the advantages of having the Duhamel integral at our disposal. So we start with the general formula for Duhamel's integral. We plug in our P of tau, which is simply P naught, right? Because our loading is constant. Keep in mind we're starting from 0. And then we plug in our unit response function, unit impulse response function, which is this one. And that is the same for all, right? As long as it's an undamped system, we can use that general form. And then we take the constants outside. We evaluate the integral, which is fairly simple. And we take the difference from 0 to t, and we get the solution. So much more simple to evaluate this particular case, right? So make sure you're familiar with how to do this particular derivation. Now let's look at ramp loads. A ramp is defined as simply a linear function increasing from 0. And usually to make this somewhat easier to express, we define that it reaches some value P naught at some time t sub r. And so expressing that analytically, we have the function is, again, we always have to emphasize that it's 0 before time 0, and then after time 0, it is equal to P naught times t over tr. So moving over to the response or the solution to this forcing function, we have what you see here, where we have a static displacement amplitude times a linearly varying term t over tr minus some oscillatory term, right? Keep in mind that in this case, UST naught is a little bit tricky because it is actually the same as before, P naught over K. So it's simply the static displacement amplitude. To get the actual static displacement, you actually have to multiply that by T over TR. So what is being shown in the figure here is actually the static displacement over the static displacement amplitude, right? Which is essentially the same as saying T over TR. All right, so look carefully at section 4.4 in Chopra to make sure you understand this nuance, okay? Do not assume that UST naught is a time varying function. It's actually always going to be a constant value, all right? But in essence, what we have is a function that is oscillating around a linearly increasing term. All right, so in this case, we're just going to hop straight to Duhamel's integral derivation for the undamped case, because as we've shown, it's a lot simpler to apply. And so here's our basic equation of motion. We've got a forcing function that is a function of t. And we're just going to plug that forcing function into the integral, right? So that's our p of tau, right? That means that we just have tau left in the integral here. And our impulse response function is the same as usual. Okay? In this case, you need to actually apply integration by parts, because now you have 2 taus in the integral. All right? And doing so, I will leave it to you to follow the steps here. You end up in this equation, okay, which is the same as what we showed above. Just a different form, but keep in mind that again, Chopra chooses to use this as your static displacement amplitude. The point is that that value should be always constant. So let's look at how to describe more complex functions using these step and ramp loads. And the best way to do that is through a practical example. So let's pretend we're going to perform a static base shear test on a single story moment frame. The idea is we want to just apply a static force P0 using a linear actuator. However, this force needs to be ramped up, so it needs to have some profile that looks like the function you see here at the bottom, right? We're going to start at 0 and we're going to go to P0 in some time tr. The question is, if we do that too quickly, we risk basically sending an impulse, or we risk exciting the system dynamically, right? So the idea is to try to avoid that and find how quickly we can ramp it without exciting too much of the dynamics of the structure, because in essence here what we want to do is we want to just test statically. And all we really need to know is what the fundamental period is of that structure. So let's say we've measured that to be 0.5 seconds. And we're going to assume that damping is negligible. And what we want is we want a TR that will give us less than 10% dynamic displacement relative to the static displacement. In other words, it should not oscillate more than 1.1 times the static displacement amplitude. We're going to do 3 things here. First, we're going to look at alternatives for describing the response in terms of the building blocks that we just talked about. We could use Duhamel's integral, but we're going to avoid that because it's a lot more computational intensive. The point of having the responses to ramp and steps is that we can quickly build more complex responses from those. And then we're going to go to MATLAB to look at how various values of TR would impact the dynamic displacement or the dynamic effects. And finally, we're going to look at how the maximum displacement behaves as a function of TR. So I encourage you to look at Chopra if you want a more analytical view of 2 and 3. The book derives essentially the same example completely mathematically, but I think using MATLAB and using visualizations is a lot more instructive and a lot more conceptual and kind of avoids too much math. So let's look at options to use ramps and steps to describe that more complicated loading function. Right, so what we're after is a function that looks like this, right? ramp and then levels off at p naught. And the leveling off starts at time tr. That's the function that we want. And so the first option might be the most obvious one. We just express this as a ramp and then a step. So essentially, we would do something like this. We would describe this as first a ramp that stops at time tr, and we would add to that a step which starts at time tr. Okay, so we know the solution to those two functions. And so we could simply solve those two independently and then sum them together. We would need to consider the time shift for the step, but that's not difficult. So the idea would be we would solve for that first function. We would forget about anything that happens on this side, right? And then we would switch over to the solution for the second one. So essentially, we wouldn't care anything on this side. We would just simply switch from one solution to another. The problem here is that we cannot expect that the system simply would switch from one to the other. There are dynamic effects, there is a certain memory in the system, and so therefore there should be some free vibration component left over from that first solution, right? And so we need to consider that. So we need to consider what were the final conditions in that first function and treat those as initial conditions in the second case to account for any remaining dynamic effects. So at time tr, we would also have some sort of free vibration component. Right? So that's a little tricky, but that's what we have to do if we're going to switch from one solution to another. The second option is to try to avoid that problem, and it requires a little bit more creativity, but it's still pretty easy to formulate. So in this case, again, let's start with our target function, which is a ramp and then a step. In this case, we're just going to define functions that exist over all time. We're not going to switch from function to function, and that gets rid of this issue of the free vibration. That's already incorporated into the solution. And so that makes things easier. So in this case, we're just going to take a ramp, same as before, but we're going to allow it to continue. So we're going to keep that solution over the entire time that we solve for. And then instead of adding a step, what we're actually going to do is we're going to add a negative ramp, right, with the same slope, right? This ramp has a slope of p naught over tr. This will have a slope of negative p naught over tr. And it will be 0 before that. And so we get the same resulting function, but in this case we can simply solve for 1 for our entire time period, let's say from 0 to t, wherever that will be. And then we can solve the other one from tr to t, and then add them together. And because we didn't simply jump from one solution to the other, this idea of the free vibration is already incorporated into the solution and can be a little bit easier to solve. Now, of course, there's additional options here. The third option would be Duhamel's integral. And you can see what that would look like here. But we're not going to go too much into detail here. This is really more for the next chapter. And you could also do differential equations, essentially, solve using EOMs as well. But again, these are not recommendable because they take a little too much effort, and the whole point of building these analytical functions for step and ramp loads is that so we can take an approach more like option one or option two. Okay, so now let's hop over to MATLAB and complete the rest of the example. Now I've provided you a code very similar to this, but with some things left out for you to fill in. And the overall goal here is to use a combination of ramps, steps, and free vibration to get to the more complex loading function that you have in the exercise. So in this case, these functions are defined straight in the code using what we call anonymous functions. I'm going to run this. Basically, the syntax gives a set of input variables and then defines the output based on those input variables. We're going to have to define a set of system parameters, which the code will ask you to do. This is simply defining the natural period in terms, defining the natural frequency in terms of the natural period. And then we can actually test some of these functions just to see what they do. So ramp response, I'm giving it a TR equal to 0.2. I'm giving it the natural frequency of the system, and then I'm just giving it a time vector that goes from 0 to 3 seconds in intervals of 0.01. If I plot that, this is what it looks like. An oscillating ramp function. Step response only needs a natural frequency in that time vector. If I plot this, that's what it looks like. Oscillations around 1. Again, these are all undamped solutions. And the free vibration just requires a natural frequency, initial displacement, which is 1, and initial velocity, which is 0 in this case, and a time vector to solve for, and that should give you something very similar to the step, except this time it's around the 0 point. So at this point, I recommend you pause the video now that you have some understanding of what these functions are doing, and try to solve the rest of the exercise on your own using the code you've been provided. You can use either option 1 or option 2 to try to solve. You've got all the functions. In this example, I'll actually show option 2 because it's the easier one and it's the one I recommend. So go ahead and pause the video, give it a shot, and then come back when you're either done or need a little bit of extra guidance. And I'll give you a couple of other points to stop in as well, so you can kind of keep working through the problem. Okay, so if you're back, let's look at how I implemented this loop. I've defined a set of rise times, and I've done this in a way that I've scaled it by the natural period of the system so that I get essentially the same results that Chopra has in the book. My time vector is defined as it was before, and I have this placeholder here for storing the values of RD, which will be my maximum displacement values essentially. But since we're looking at normalized values, this is simply just an amplification factor, which is why I'm calling it RD. Now here's the key part here. I've defined first of all a positive ramp U1, which is simply my ramp response with the corresponding slope, right, TR, and the natural frequency of the system, and the time vector, which is just going to be unmodified here. And then my second ramp is my time shifted negative ramp. And so all I do is I negate the ramp response, my slope, right, and my natural frequency stay the same, right? This is a property of the system. And then I shift my time vector by TR, right? That will give me, by minusing TR, that gives me a positive shift, right? Because the ramp is defined for all time, I need to force it to be 0 before time tr, and that's what I'm doing here. I'm setting any value of u2 that for time less than tr to be equal to 0. And my final response is simply the sum of those two responses, right? So pretty straightforward. Really, this line is the tricky one. And I've already defined this for you, but that static displacement, like I mentioned in the presentation, is T over TR. And that goes until time TR, and then again here I'm forcing every value after TR to be 1 because that's where it levels out. And then this value defines my maximum limit, right, which is simply 1.1. That means 10% over the static displacement. My RD is simply the max U value, so that's pretty easy to implement. Okay, so let's run this and see what that looks like. The rest of the code is just for plotting. So I'm going to run this code. It's going to generate 6 figures. So looking at these 6 figures, we start with the longest rise time on the left and go all the way to the shortest rise time on the right. We see that for a slow rise time, a long rise time, the oscillations are close to the limit, but they do exceed it. When the rise time is exactly 2, the oscillations actually at the peak go straight to 0. And this is actually because the force levels out exactly at the peak of that oscillation, meaning that the velocity at that point was exactly 0. And so it's almost like saying that your initial conditions, right, were 0, and so this levels out. As we go faster, the oscillations do start to get larger though. So notice how 1.5 is much larger than 2.5. Again, we have a similar behavior when we have both TR and TN the same. It's very similar to the case of the ratio being equal to 2, except this time there's only one oscillation before it levels out. And again, when we go to 0.5, the oscillations get larger, and at 0.2 they get larger still. So we have a general trend, as you can see, as the rise time gets faster, the oscillations get higher, which makes sense because if you think about it, as that TR tends to 0, the input function tends to a step input. And if you look back at the step response, you will see that it will go from 0 to 2, right? So it'll be 100% greater than the static displacement. But we have those exceptions. When the ratio is exactly equal to the period, we'll get actually no displacement, right? So the answer to the question is really the fastest we can move it is TR over TN equal to 1, or TR equal to 0.5. All right, so let's go back here. And now what we'd like to do is, instead of looking at each of the plots separately, I'd like to look at just the maximum displacement as a function of TR. All right, so this is what we're doing here. We're going to plot just the maximum for each of those 6 plots that we generated. And we see essentially what we observed, right? So it's very high for 0.2. It goes down towards 0.1, where it goes, towards 1, where it goes to 0. Goes up again, goes to 0 at 2, goes up slightly, but the overall magnitude tends to decrease as you go towards the right. Now, we can actually try to generate a much more higher resolution plot, but to do that, I'm actually going to comment out the plot so we don't generate a ton of plots, and I'm going to set this to go from 0.1 in intervals of 0.2 all the way up to, let's go to 5. So I'm going to rerun this and then run this function. That didn't work so well. Let's try it again. Let's have a finer resolution here. There we go. So that worked a lot better. All right, so now we see a more continuous looking function. So essentially what we see is several lobes, right? So at every integer multiple of the period, we have 0, but the overall shape of this function is decreasing somewhat exponentially, okay? You will notice that Chopra actually derives this function analytically, which is something I would expect you to be familiar with, but not necessarily to be able to do on an exam.